All right, hello, we got some more forces questions. We're starting here with a definition of density. So it's the mass of an object divided by its volume, divided by its volume. So a simple 1 mark definition thing. You should always be picking up the marks for those. Figure 2.1 shows the variation of density of the Earth with depth from the surface. Right, so we've got the surface here and it's going downwards. Suggest how figure 2.1 shows that the Earth consists of a number of distinct layers. Right, so there are sudden changes or step changes, sudden or step changes in density. At these two depths at 3 times 10 to the 6 meters and whatever that is, 5 and a bit, say 5.1 and 5.1 times 10 to the 6 meters, suggesting change in material. So that's that bit. I mean, there's lots of different ways you can phrase it. Geophysicists believe that the central core of the Earth is solid iron. The central core is surrounded by a layer of molten metal, which must be this bit. Central core starts at a depth of 5.1. Oh yeah, that's what we had here. 5.1 times 10 to the 6 meters. Solid core accounts for 18% of the mass of the Earth. Mass of the Earth is 6 times 10 to the 24, and its radius is that. Calculate the mean density. Right, so we want to do mass over volume. So we've got a 0.18 times 6 times 10 to the 24. That's the 18% of the mass that's in the middle. And then the volume is going to be 4/3 pi. And then we want the radius. Well, they've given us the depth. And where's it got the radius? Oh, there's the radius. So that's 1.3 times 10 to the 6, 1.3 cubed times 10 to the 18. So we can cancel a few bits there, and then we got a little bit less to put into the calculator. So what have we got here? 0.18 times 6 is 1.08, as you'd expect, divided by pi divided by 1.3 to the power of 3. That's that bit. Then we got divide by 4 is that. Then we got to multiply by 3, which ends up giving 1.17 times 10 to the 6. So we'll say 1.2 times 10 to the 5 kilograms per meter cubed. So that was fairly straightforward. Right, now we've got a skydiver. State 2 factors that affect the magnitude of the drag force acting on an object falling through air. Right, 2 factors. We've got our usual quartet of these. We've got velocity, we've got the surface area, we've got the air pressure or air density or air temperature, something to do with the air. We've got what the object is made of, what the surface is made of, whether it's quite resistive or not, or whether it's quite sleek. So I'm going to go for velocity and air pressure as my 2. Then we've got a 75 kilogram skydiver falling to the ground. Air resistance, drag force D is given by this equation. So that's nice that they've handed that over. First part, draw arrows to represent the weight and drag force. So weight downwards, as always, drag force opposing the motion, as always. Calculate the weight of the skydiver, right? So they said it was 75 kilograms. So W is going to be 75 multiplied by G, which is coming out as 736 newtons. So I'll say 740 to 2 significant figures. What's next? At a particular instant, the speed of the skydiver is 20 meters per second. Calculate the instantaneous acceleration of the skydiver. So at that point, So at 20 meters per second, d is going to be equal to 0.3 times 20 squared. So that's 400 times 0.3, 40 times 3 is 120 newtons. So when we do our Newton's second law on this, we're going to have 75g minus 120 is equal to 75 times a. You'll note here I've gone back to 75g rather than taking the 740 from there, because otherwise we're just pushing rounding all the way through. We don't want to over round these things. So 75 times 9.81 minus 120 is equal to that, divided by 75 gives us 8.21. So A equals 8.2 meters per second squared. State the relationship between the forces W and D when the skydiver reaches terminal velocity. Well, the whole point of terminal velocity is we're going as fast as we can go. We don't have any net force anymore. We have no acceleration. So, and that is when W equals D. That is the point of it all. And now they want us to determine the terminal velocity. So we must have a drag force which is equal to W. 75g is equal to 0.3 v squared. So 75 times 9.81 is equal to that, divide by 0.3 gives us a big number, and then square root that. We've got 49.5 meters per second. 49.5. So yeah, these terminal velocity ones, they're very repetitive. They don't mix them up very much. And maybe one day someone will come up with something a bit more imaginative. Right, so from skydiving to space. First of all, they want us to define what the Newton is. So don't just write out, something like this. This is a fine starting spot to say 1 Newton is 1 kilogram meter per second squared. But you want to actually write out something along the lines of 1 Newton is the force required to accelerate a 1 kilogram mass with an acceleration of 1 meters per second squared. So yeah, actually write it out. That is the force required to accelerate a mass at that particular acceleration. So there you go. Right, now we're on to looking at this spaceship. They've given us a picture of a spaceship just in case you can't think of what they look like. Mass of the spaceship is 1.9 times 10 to the 6 kilograms, and during liftoff we've got this upward force, quite a big upward force. Calculate the weight of the spaceship. So the weight of the spaceship is just going to be 1.9 times 10 to the 6 multiplied by, oh, my screen's frozen, multiplied by g. And that comes out 1.86 times 10 to the 7, but we're only 2 sig figs on all this. So I'm going to do 1.9 times 10 to the 7 newtons. So, but it was a 1.86 times 10 to the 7. We do that to 2 significant figures. Then calculate the initial vertical acceleration as the spaceship lifts off. So on the upside, we got a 3.1 times 10 to the 7. That's what's been pushed upwards. We have to take off the 1.86 times 10 to the 7, and that is 1.9 times 10 to the 6 multiplied by a. So all in all in this, we've got, what is that going to be? That's going to be 1.24, 1.24 times 10 to the 7. Then we need to divide by the 10 to the 6, divide by the 1.9. So we got 12.4 over 1.9 is the acceleration. 12.4 divided by 1.9 is 6.526. So 6.5. I'll put down first of all 6.53, which equals 6.5 meters per second squared. Okay, the vertical upward force on the spaceship stays constant. Explain why the acceleration of the spaceship increases after liftoff. Right, there's a lot of things you could do here. We could say fuel being used, so being used, therefore mass decreases. We could say further from center of Earth, so therefore G decreases, and therefore W decreases. That's all the same sort of thing. What else could we have? If they said anything about air resistance, we could have less air resistance. So yeah, we got options here. I mean, all these things help when you've got a rocket going up in the air. You get thinner air, you get a lower force due to gravity, and the rocket gets lighter. So all good. Right, this is the last one in the set, and then we're done for our forces block. This looks like it's going to be a moments question. So figure 6.1 shows two equal but opposite forces acting on an object. Okay, so we've got a couple. The point O is at a distance x from the nearer of the two forces. Right, they've marked that on here. Separation between the two parallel forces is 3 centimeters. Yeah, which they've marked on. Determine the torque of the couple exerted on the object. So that is going to be the one of the forces multiplied by the separation, which I'm going to flip over to meters because it's just more normal to do that rather than having Newton centimeters, and it's quite an easy multiplication to do. So 0.12 Newton meters. Calculate the total moment of the forces about the point O and state the significance of this value. Well, we know it's going to be the same because it doesn't matter where you calculate the torque of a couple about. It can be any point. So we know we're going to get the same, but I'm assuming here they're wanting us to actually go through the motions of doing this. So that's 0.12 Newton meters clockwise. We can do a similar, so if we're doing clockwise here, we're going to get 4 times x plus 0.03, keeping it in meters, minus 4 times x. That's going to be our, again, clockwise moment on this. So the 4x's are going to cancel and we're going to be left with 0.12 Newton meters clockwise, which is what we had previously. So we can say it's the same, and we can then say it's independent of x, which is the interesting part of it, I suppose. Right, part B, state 2 conditions necessary for an object to be in equilibrium. Right, so we need translational and rotational equilibrium. So we're going to have to put both of those down as no net force and no resultant force might be. I know it's the same thing, but let's have no resultant force, no resultant moment. I feel like saying resultant today. So one of them means we're not moving through space, we're not translating the center of mass. The other one means that we're not rotating it. So there are 2 things we need. Concrete paving slab has a mass of 45 kilograms and dimensions of those. Calculate the density. So density is mass over volume, so 45 over 0.6 squared times 0.05. Type all of that in. This could be quite a nice number. 2500 kilograms per meter cubed. So that was fine. Right, now we've got figure 6.2 shows the concrete paving slab in equilibrium. Okay. So it's being held up at one end. 2 forces acting on the slab are shown. So they haven't said anything about P. That's going to be where we're going to want to take moments. The weight of the slab is W, which is 45G. And the force F is applied at right angles, great, to the end of the slab. By taking moments about P, determine the size of force F. Okay, so they've given us that distance, right? Okay, I was beginning to look around to see if we had a uniform slab or not, but it doesn't matter because they've given us the perpendicular distance here. If we didn't have that distance, we'd be thinking, well, is the center of mass actually 0.3 of a meter along? But it doesn't matter. We don't need the angle because we've got the perpendicular distance of both forces. That's the useful thing with moments that often people forget. you don't have to take the moments along the same line. Okay, we're taking moments about P, but that doesn't mean to say we have to measure all of our distances along the same line, like the line of this this slab. Providing you've got a perpendicular distance for each force, then it's fine, because we're just, the angle that we'd be using here with a theta would be the angle that we'd be using here for a theta. So it doesn't matter whether we've got this component of the force or this component at a distance. Everything works out fine. So we know that we've got to have 45g multiplied by 0.15 has got to be f multiplied by 0.6. So f is going to be equal to a quarter of 45g. 45g over 4. Right, let's just type that in. We've got 45 times 9.81 is equal to that, divided by 4 is 110.36, yada, yada, yada. So 110 newtons. Yeah, so a nice way to round off.